Just want to talk about a couple of things before I actually start the notes for the probability unit. It's a pretty short unit, so you need to take a look. We're already testing May 8th. Notice you have a quiz May 3rd, and I also want to point out in some color right here is that there will be no retakes in this chapter. So you need to make sure that you're keeping up on this with that understanding. Okay, so what we're going to do is we're going to start some notes. This should be familiar to you. I believe that you guys have seen this before. So pause the video, do the warm-up, see if you can figure it out, and then we're going to go over that super quickly. Okay, you're back. So our learning target for today is to solve problems using the counting principle. So here's what we're going to do. We are going to talk about Jamie wants to buy a new car, and he's chosen a model, but he still has between automatic, which I would get in Crystal Lake, versus transmission or manual, sunroof or no sunroof, red or white or black. So how many different types are there? Now, I know some of you have went through this before, so let's take a look at, he knows the make and model, but the types of transmission. There are 2 types of transmission. And there are 2 types of sunroof or no sunroof. And then there are 3 colors. So if I multiply all of those independent choices together, it gives me a 12. Now, I am guessing that some of you have seen that before. I'm going to go back and we're going to talk about something called sample space right now. And sample space is just we use set notation for all of this stuff, and we can make tree diagrams here. So I want you to see what we just did above. You could start off with his car because we know the make and model. And from the car, we can either have our automatic or we can have our manual. And with that, if I can spell manual, sorry about that. And then after we have auto or manual, we can see that we can have a sunroof or no sunroof. And I could have that for the automatic, and I could have either a sunroof or no sunroof in the manual. And then I could pick red or white or black in the sunroof with the automatic, or red or white or black for the no sunroof, or I could pick red or white or black, and I think you guys are getting the idea, red or white or black. So if I count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, can you see you come up with your 12 combinations? Now, I did the tree, my sample space here, or my tree horizontally. You can put them vertically and start up here with the car and then go this way. I'm not going to draw it all out. I think that you guys get that kind of stuff. Okay, so on to actually having some kind of a theorem that goes along with this, or a principle that goes along with it. So if counting principle states that if one event has P possibilities and another event has, this should have been a Q possibilities, the number of ways both would occur would N would equal P times Q. Now, N, just so I get some notation out there, N means your number of outcomes. So you guys need to know your notation. N is my number of outcomes. P and Q are my individual events, and they don't distract each other. So counting principle can be easily used to answer many different types of cars that he had. So N, just going back to that first example, he would have 2 types of transmissions times 2 types of sunroof options. times 3 types of colors. And again, we came up with 12. So let's take a look at the first example. For the first example, it says how many 4-letter patterns can be found using U, V, W, X, Y, and Z. So the first thing that I looked at is I have 6 choices here. If the letters can be repeated. Now, 1, 2, 3, 4. Sorry, that's not super straight. I have 6 choices for the first spot. I have 6 choices for the second spot. I have 6 choices for the third spot, and I have 6 choices for the fourth spot because these are considered independent. This one does not affect this one, and so forth. So if you have 6 choices, 4 events, that actually gives you 6 to the 4th power, which turns out to be 1,296. So now let's take a look at the exact same thing, but this time they may not be repeated. These are dependent upon each other. So 1, 2, 3, 4. Okay, so the first one, I have 6 choices. I pick one of the letters. It can't be repeated, so now I only have 5 choices. Pick a letter. Now I only have 4 choices. Pick a letter. Now I only have 3 choices. So when it is dependent on each other, when what I pick in spot 1 affects spot 2, and so forth, that is called dependent. And look at how it cut down the number of choices. Okay, so we have just a whole bunch of different types of probability. And if you guys like, turn off the video, do all of them, come back and check these, and I'm going to go over them. So stop, and you guys can check if you need help. Are the answers all given on these? So if you get them all right, you don't have to come back to the video. If you don't get them all right, come back to the video because that's what's going to be on your homework tonight. So stop. Okay, welcome back. So I'm asking you how many 2-digit numbers can be formed from 1, 2, 3, 4, 5 if repetitions are allowed. So I have 2 spots. That's 5 times 5, or that's 5 to the second, which is 25. Okay, so how many ways can 5 different book arrangements be on the shelf? So I have a pile of 5 books. I'm going to put them on the shelf. Order matters in this case because I have 5 choices for the first spot. 1 book's been used. Now I only have 4 choices for the second. Another book's been used, so now I only have 3. Now I only have 2. And now I only have 1. So there are 120 choices for me to put the books on the shelf. So for number 7, how many 7-digit numbers can be formed through the digits 0 through 9? This is the spot where most people goof up. 0 through 9 mean I have 10 choices. So please make sure that you guys get 0 is included in there. 0 is the first choice, 1 is the second choice. 10 choices in that case. Okay, so I have 1, 2, 3, 4, 5, 6, 7. I have 10 choices, 10 choices, 10 choices, 10 choices, 10 choices, 10 choices, and 10 choices, or 10 to the 7th power, which turns out to be 10 million. Okay, so sample space. Yes, you are going to have to write out sample spaces. This could be a problem on a test. So as I do this, list all the sample spaces that you can flipping a coin. So a coin, 3 times, the coin itself has 2 choices. You either have heads or you have tails. And I think it's easier for me to, since I got to do the sample space, to go through some kind of a pattern. Now, I personally start with 1 letter in all spots. Heads, heads, heads. So from there, I'm going to change 1, tails, heads, heads. So notice only 1 change. I'm now going to move that single tail throughout the grouping here. So now tails is in the middle, and finally tails is at the end. So a single tail has been moved throughout. So then I'm going to start with 2 tails and a heads, and now I'm going to move that throughout. So tails, heads, tails, and then I could have tails, oops, I'm sorry, I goofed that up, heads, tails, tails, and then my last one, which was what I was looking at, was tails, tails, tails. So when I look at that, my sample space has 8 choices or possible solutions, but the sample space itself is all of that writing. Okay, so taking a look at letter E. From the letters A, E, I, O, R, M, N, how many different 4-letter patterns can be formed if no letter can occur more than once? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. I have 7 choices. I have 7 choices for the first spot. I use a letter. I have 6 choices, 5 choices, 4 choices. They depended on each other. What I picked here affected this. But now, for the next one, I'm going to have a little more parameters on this. Out of my 4 letters, it says the first letter has to be a vowel. So 1, 2, 3, there's only 4 vowels out of the 7. 4 choices. One of the vowels is picked. Now, the last letter has to be a consonant. Consonants, not vowels. 1, 2, 3. There are 3 choices for the last spot. One of them gets picked. The rest of them I could care less. So how many letters do I have left? 1, 2, 3, 4, 5. So I have 5 choices and then 4 choices. And I multiply those all together to come up with my 240. Okay, so how many ways can 5 cars be parked along the street if the only SUV is in the middle? So 1, 2, 3, 4, 5. There's only SUV is here in the middle. So it has only one choice to go through. So I am now down to 4 cars left. So I have 4 choices, 3 choices, 2 choices, 1. That one SUV locked out how many of the rest of them I could have, and that turns out to be 24. Last page of different examples that you could see. This one is asking how many ways can 6 books be arranged on a shelf if one of the books is a dictionary and it must be on an end. So 1, 2, 3, 4, 5, 6. Here is the dictionary. It has one choice. That means I have 5, 4, 3, 2, 1 for that. And I work that out. That gives me 120. But that's not the only end. 1, 2, 3, 4, 5, 6. There could be a dictionary here. Then there's one choice, which gives me 5, 4, 3, 2, 1, which also equals 120. And I add these together, and my final turns out to be 240. For letter I, using the letters from the word equality, how many 4-letter patterns can be formed in which Q is followed immediately by a U? So here, this one goes up a little bit. This is a little bit harder. So I've got 4 letters. So first of all, I need to look at, I have 1, 2, 3, 4, 5, 6, 7, 8 letters. So the first one can be a Q and the second one has to be a U. If I use the Q and the U, I had one choice. That leaves it as 6 and 5. But is that the only spot for the Q? No. I could have, the Q and the U being here in the middle because the directions just say have a Q followed immediately by a U. So there's still one choice here and there's one choice here. There'd be, 6 choices for this one and 5. And is that the only spot where the Q and the U could go? No, the Q and the U could also go here. I still have one choice. This is 6 and this is 5. The U can't go at the end because I can't have the U immediately follow it. So this is 30 plus 30 plus 30. That gives me 90 total choices. Okay, the last one is just writing, or the last two are writing some sample spaces and making sure that you understand it. Now, I personally, if I'm rolling 2 die, first of all, everyone understands there's 6 sides to every dice. So, every die. So, we're going to have numbers 1 through 6 represented here. So, this is kind of how I organized it. I had 1, 2, 3, 4, 5, 6. That's the first die. The second die is 1, 2, 3, 4, 5. I'm going to squeeze in that 6, going that way. So now, and I'll try to color this. You got the 1 from the first die. You got the 1 from the second die. That is one combination. You've got the 1 from the first die and I could have let me redo this. I've got 1 and 1, and that could be my outcome. I could have a 1 and a 2. I could have a 1 and a 3. I could have a 1 with a 4. I could have a 1 with a 5. And I could have a 1 with a 6. I technically don't know which die is 1 and 2 unless I say that. And it said that I'm rolling 2 distinguishable ones. So that's why I have to look at this. 2 rolled with 1, and 2 rolled with 2, and 2 rolled with 3, and 2 rolled with 4, and 2 rolled with 5, 2 with 6, 3 with 1, 3 with 2, 3 with 3, 3 with 4, 3 with 5, 3 with 6. I think you guys get that you have an idea of what the patterns are supposed to be. Here's the thing. 1 for the first die, 2 for the second die is different than 2 for the first die and 1 for the second. So it depends on which number comes up, not which die put it on there. So in this case, I'm going to say order mattered. Did the 2 get rolled first or did the 1 get rolled first? Order matters. So now, when you look at your last one, when they're indistinguishable dice, you can't tell them apart. Okay? Ooh, that's sloppy. 1, 2, 3, 4, 5, and 6. And 1, 2, 3, 4, 5, and 6. You roll them, you get a 1 and a 1. Okay, we got it. Second one, I have a 1 teamed with a 2. And that's going to be the same as 2 teamed with 1 because I can't tell which number is which. So 1 with 3, 1 with 4, 1 with 5, 1 with 6. This spot right here is the same as this spot here. So I'm going to skip that and I'm going to start this column with 2 with 2, 2 with 3, 2 with 4, 2 with 5, 2 with 6. So now on the next row, 3, let me erase that. 3 with 1 is the same as 1 with 3. And then 2 with 1, 3 with 2 is the same as 2 is 3. So in this case, I start with 3 and 3, 3 and 4, 3 and 5, 3, and 6. Notice order doesn't matter. So for the next one with the 4s, this spot 4, 1 is the same as this. 4, 2 is the same as this. 4, 3 is the same as this. So I am going to start with 4, 4, 4, 5, and 4, 6. Ooh, I should have made it blue. And then the same idea with the 5s. These are the same. This is the same. I'm going to start with 5, 5, and 5, 6, and finally 6, 6 for my last one. Notice this cut down my sample space. There's not as many here. I am going to say that order does not matter. And this is going to lead into some of our permutations and combinations that we do tomorrow. So you've got everything done now. Go out, do your homework, get it done quickly so you don't have to take anything home tonight. Have a great weekend.